Today we will be discussing about voltage stability or voltage collapse. They are almost similar terms which are used interchangeably. A voltage is stable, then that system will not collapse, and if the system is not stable, then the system will collapse. So voltage stability or voltage collapse are almost the same thing. Just voltage stability means system is stable, and collapse means system has collapsed and cannot be recovered. So this is the major difference, but they are interchangeably. So the voltage stability is a steady state problem which involve the steady state power flow studies. And generally when we are talking about voltage, we are discussing again and again that voltage means reactive power of the system. So the voltage stability will indicate the transfer reactive power from the source to sink. What is the ability of the system to transfer the reactive power from source to sink? Generally, we have heard about a term maximum power transfer. So maximum power transfer limit for a power system is not equal to the voltage stability limit of the power system. So they are two different. In some of the cases, it may be that maximum power transfer limit will be equal to voltage stability limit, but generally they are different terms and they are not indicating the same concept. So when we're defining a power system, there are a lot of definitions which defines a power system stability. Some of them I have discussed or identified from them. One is that a power system at a given operating state, when a small disturbance occur in the system, voltage stable, the system will be voltage stable if for a small disturbance in the system, voltage near the load will be identical. That means the voltage is not changed across the load terminals. Then for a small disturbance, that power system is said to be voltage stable. Second definition says, in a power system, if a voltage near the load approaches past disturbance equivalence value after disturbance. That means when a disturbance is occur in a power system, if the load voltage again gain or reach to the post disturbance equilibrium value, then that system is said to be voltage stable. That means after the stable and before the stable, if after transient period, if the system will be able to regain the voltage, then that system is said to be voltage stable. Next is the voltage collapse. If the post disturbance equilibrium voltage are below acceptable limit. That means if the system is not able to regain the previous value of voltages and the voltages is not accepted limit, then that is known as a voltage collapse. That means that system has collapsed and voltage is now not in the acceptable range of the system. So the voltage collapse indicates a system instability, or it indicates the reduction in the voltages in the system. Voltage collapse generally happen in the following cases: when we have a heavy loaded transmission line, when we have a faulty line, or when we have a reactive power shortage in the system, then voltage collapse will occur. The transmission of real or reactive power is limited because of the following limitations: that high reactive power losses happen in a heavily loaded lines. If the lines are heavily loaded, their reactive power losses are more. And we have limited action of VAR compensation, then the real power transmitted by the system is limited in the transmission lines. So reactive power demand increase due to either increase in the load or motor stalling. That means more and more motors are coming together in the power system and motor load is increasing in the system. Then your reactive power demand of the system will increase. Now, why voltage collapse happen in a power system? Voltage collapse happen due to the various aspects. Some of the issues we have chalked out, that the voltage collapse can be happen due to the increase in the inductive load of the system, which will increase the reactive power of the system, and due to increase in the reactive power, the system is not able to recover. Then second major concern is on load tape setting of the transformer operation, that is OLTC operation. As we have discussed in the previous class, the major issue of voltage collapse is due to the on load tape setting of the transformers. That if the line outage happen in the system, that means the line is, one of the line is not available, then there will be a possibility that for maintaining the system voltage, a corrective action can happen and the line will collapse. And if one of the generator fails, then again there is a possibility that voltage will collapse. And due to the load recovery dynamics, we can also have a voltage collapse situation. And if we have limit of reactive power compensation and reactive power generators, due to that also the voltage collapse can be in the system. So now what we are doing to reduce the possibility of voltage collapse? So first, to reduce the voltage collapse, switching of shunt capacitors are done to increase the reactive power generation in the system. Then second operation, which is generally not feasible, that we will be blocking the OLTC operation. That means we will block or we will not do the tape settings operation in a power system. Then we have a generator rescheduling. Due to this rescheduling, we will decide or reschedule how much power will be supplied by the one generator, and due to this we will be rescheduling the reactive power load on the system. Then we can also do strategic load shedding. That means we will remove load in a strategic manner so that the system reactive power does not affect it much. It will be in a small disturbance changes, and due to that the possibility of voltage collapse can be reduced. Or we can increase the reactive power generation of the generators in the system, so the reactive power requirement of the system can be met and the possibility of voltage collapse will reduce. So when we talk about voltage stability, so in general terms, a voltage stability of a power system is the ability of a power system to remain in a state of equilibrium during the normal conditions and also to restore an acceptable state of equilibrium after the disturbances. As we have discussed, if the system is able to regain the voltage, then that system is stable, and if it is not in the acceptable limit, then that system is voltage unstable. So a voltage power system is said to be voltage stable if it remain in a state of equilibrium during the normal conditions and also to restore an acceptable state of equilibrium. We are saying acceptable because it is generally not possible that we will reach to the state similar to which before the disturbances. So if there is a in the acceptable range, then that system is said to be voltage stable. So the term voltage instability is also we have to define. So the voltage stability means a power system to become unstable during the voltage reduction due to the outage of many equipments. A power system to become unstable. If a power system become unstable during the voltage reduction, can be due to the outage of many equipments like generator, transformers, bus bar, or weakening of voltage control system, or it can be decrease in the production of reactive power. So the power system will become unstable in all these due to all these effects, then that system will become voltage unstable. And the load dynamics to restore power consumption is just beyond the capacity of the capability of the power system. That means when the load change, the ability of the power system to restore the power consumption is not possible for the power system capabilities, so the system will become unstable. So the power system stabilities are classified on various aspects. One is on the basis of the time scale. So time scale means it is a short-term stability or it is a long-term stability. They are also defined at due to which that stability is affected. It is generator driven or it is a load driven. So if it is a generator driven or it is a load driven, so we can have various stability which we define for short term and long term. If we talk about generator driven, then it is a rotor angle stability or steady transient state stability. And when we are talking about generator driven long term stabilities, it is a frequency stability of the system. And if we are talking about short term load driven, then they are short term voltage stability. And if we are talking about long term load driven, then they are long term voltage stability. That is due to small disturbances and due to the large disturbances. So these are the various stability, voltage stability which we are handling in the power system. So when we are talking about steady state stability, the steady state stability is the stability of the system for small disturbances in the form of undamped oscillations. So if the system is stable for small disturbances, then that system is known as steady state stable. And if a system will be unstable for small disturbances, then that is steady state unstable. When we are talking about transient stability, so transient stability is due to the lack of synchronizing torque by large disturbances. So when we are talking about transient stability, we are discussing about large disturbances which are happening in the power system. And due to that large disturbances, we have not have enough synchronizing torque which will synchronize the power system to operate in stable condition. And then if we are talking about load disturbances, then we have a short-term voltage stability. Short-term is for a small duration, and it may be due to the operation of induction motors, or it is maybe due to the excitation system of synchronous generators, or it may be due to the operation of the various compensating devices like TCR, TSCS, SVC, or UPFC. And when we are talking about long-term voltage stability, they are due to the operation of OLTC, tape settings of transformer, delayed action in load restoration, and delayed operation in corrective action of compensating devices in the system. So these are the long-term voltage stability is due to these parameters. And when we are talking about long-term long-term voltage stabilities, we have small disturbances and we can have large disturbances. So when we have small disturbances, we have control voltage after small disturbances. If we are able to control the voltage after small disturbances in the power system, then system have small disturbance, long-term stability, and that can be an example of small disturbances is change in the load. And when we are talking about large disturbances, then it will be the control of voltage after large disturbances. So large disturbances are faults in the power system, switching operation of power system, or the load or generators loss in the power system, then it will be in the large disturbance which will occurring in a power system. Change in load is small because there is a small change in load, and if the load is disconnected by this in a system, then it will be a large disturbances. So these are the various stabilities which we define with respect to power system. The voltage collapse, when we are using this term voltage collapse, it generally referred to large disturbances. It is not generally referred as small disturbances of power system. So the voltage collapse is usually involved large disturbances and is mostly due to the reactive power deficit in the system, and due to this reactive power deficit, the voltage is not able to maintain and voltage will collapse in that system. So when we are talking about voltage collapse, we have transient voltage stability and we have steady state voltage stability. So when we are talking about transient voltage stability, we are talking for the system to be stable for a very small duration, that means 0 to 10, almost 0 to 10 seconds. If the system is able to become stable within 10 seconds of the disturbance, then that will come in the transient voltage stability. The transient voltage stability can be due to the various issues. The major issue which is due to the induction motor and DC generators operation. So if in a system we have various induction motors and we have various DC converters in the system, which may lead to the voltage collapse. This voltage collapse is because when induction motors and DC converters operate, the reactive power demand of the system increase, and due to this demand increase in the reactive power of the system, the voltage of the system will drop, and due to this drop in the voltage may collapse. Then if one of the induction motor is not able to accelerate, that means it is not able to increase or decrease its speed, then due to this after the disturbance, the post disturbance period, then it leads to the stalling of the adjoining induction motors, and it will also reduce the voltage of the system. The next possibility is islanding of the system. If an electrical islanding and under frequency load shedding happen in the system, then that will lead to the collapse of the system, because in that case, if the power system imbalance will become more than 50% in areas, then that system will lead to the voltage collapse due to this imbalance between the power of the areas. And to maintain the balance between the areas, the system will act, and due to this system action, the system will collapse. And if we are using a HVDC line in the system, the use of HVDC link will also affect the transient voltage stability of the power system. And when we are talking about steady state voltage stability of the power system, it is referred for a few minutes. It will be if the system is able to regain the voltage within a few minutes, then that system will be steady state voltage stable. These voltage stabilities involve high load and high power imports from different areas, which will create a large disturbance in the system, and high reactive power loss will happen in the system. And due to this reactive power loss, the voltage will dip in the receiving end, and due to that dip in the receiving end voltage, the voltage may be not within the range. And the main reasons for steady state voltage stabilities are tape changing transformer or the distribution voltage transformer sense the low voltage in the system, and it will start acting to restore the distribution voltage, and due to this act of restoring, it will start load restoring, and due to that we again have a voltage dip in the system, and due to that a voltage sag will be there, and that system will become again go to the voltage drop in the system, and this will create a issue. This issue we have discussed detail in the previous class. Then if the generators are overexcited or overloaded, then it will lead to the voltage collapse due to the increase in the reactive power loss of the system. Due to the large load demand or large rapid magnitude of the power transfer, reactive power demand will increase, and due to this demand increase in the reactive power, voltage will reduce in the system. So this is the basic cause for steady state voltage stability in the system. And generally, to remove this, we have discussed various methods, or generally the load scheduling, strategic load shedding, and use of fast acting reactive compensators can reduce the voltage instability in the power system. So this is all about voltage stability or voltage collapse. So generally, if we talk about the voltage stability or voltage collapse, is almost similar things. They are indicating almost the same concept. The difference is voltage stability means system is stable. So we can say voltage instability is similar to voltage collapse. So this is about voltage stability or voltage collapse. So this is all about this. If anyone have any doubt, they can ask.
So
So
ये
if
voltage collapse and voltage stability से questions कैसे आएंगे?
इसमें से जनरली थ्योरेटिकल क्वेश्चन ही बनते हैं, क्यों होता है, कितने तरह के होते हैं, क्योंकि अभी तो वैसे भी आपके जो होगा वो एमसीक्यू ही होना है, तो एमसीक्यू में तो ऐसे ही क्वेश्चन बनेंगे.
Okay, sir.
क्योंकि अगर हम नॉर्मल बात करें तो आपकी जो so when we are talking about computer control of power system, then we have a various load control centers in the power system which will be controlling the complete operation of power system and monitor the various condition of the system. So the energy control center energy control centers are traditionally been the decision center for the transmission and generation so these are the control centers which will be working as the decision center for the transmission and this generation of the system, and they are generally for a large power system. The energy control center provides the functions necessary for monitoring, coordinating, the minute by minute physical and economical operations of power system. So all the controlling of the power system will be done by these energy control centers. So they will decide, they will be monitoring the complete power system. That means they will be continuously monitoring what is the generation by the each generator, what is the voltage of various parts, what are the current flowing in the system. They will be continuously monitoring, and they will be regularly coordinating the minute by minute physical and economical operation of the power system. That means it will command the generating units to generate the power so that the of your power system will be working in economical operating zone, because the power system have different characteristics. On the basis of their characteristic, their generation capacity will be decided to meet the particular load demand. So on the basis of the load demand of the system, the economical operation of the power system is decided, and then it will send a signal to the generating unit for generating the power system, power according to the scheduled load. So these are the mainly the, if you can say, heart of the power system, which will be monitoring and controlling the transmission and generation of the power system. It will also decide how much power will be transmitted from one area to another area and how your transmission line will be utilized. We can have many interconnected regions. Like in India, we have different interconnected regions in the system, but there are many control areas, with each control area having its own ECC. So we can have, if India, we have generally divided that into 5 parts: eastern region, western region, middle region, northern region, and east, west, north, south, and middle region. So generally the power system of India is divided into 5 interconnected regions. But it is not that only 5 energy control center will be there. We can have many control areas depending on the requirement of the system. So for each control area, we can have separate ECC. Generally in India, in one state, there will be one load or energy control centers which will be controlling the area or load requirements of the complete system. So maintaining integrity and economy of an interconnected power system required significant coordinated decision making. So when we are talking about maintaining integrity, reliability, and economy of an interconnected power system, we require significant coordinated decision making. It is not an area will decide on its own. We have to decide for complete area, and on the basis of that complete area, we have to coordinate with each of the control area so that reliability, integrity, and economy of the system will be maintained. So the prime function of energy control center is to monitor and regulate the physical operation of the interconnected grid. So ECC main operation is monitor and regulate the physical operation of the interconnected grids. Most areas today have a two-level hierarchy of energy control center with the independent system operation performing the high-level decision making and transmission over owner. ECC will performing the lower level decision making. So generally ECC will have two parts. One is independent system operators, that are ISO, which perform high level decision making. High level decision makings. And second, we have transmission owner ECC that will perform lower level decision making. So now we have to decide what is high level decision and what is low level decisions. So when we are talking about high level decision makings, that means it indicates major decision like power generation, load on line, etc. And when we are talking about low level decision making, it will be mainly how we will be distributing the power. So which area to be connected, which area to be disconnected, how much power to be supplied to an area, that is decided on a low level, and how much power will be generated by the system, how the load on line will be compensated, and how much power will be sent from each of the line, how the buses will be functioning, what will be the frequency of the system, and how much load will be they can supply. Like these, they are high level decision makings. So when we are talking about high level decision making, so high level decision making, we have substations, we have remote terminal units, generally referred at RTU, communication link and we have energy management system, EMS. So for high level decision makings, we have various issues which we will be coordinating. We will be coordinating with substations. We will be coordinating with remote terminal units. We will be coordinating the communication links, and we will be coordinating the energy management systems. And the energy management system will provide the capability of converting the data received from substation to the type of screen we are observing, where it is displayed. The energy management system will be converting various data which are received from the various portion of the substations or generating stations, and then it will be converting to the data type which we will be able to monitor on a screen. So this is the basic philosophy of energy control centers. So for energy control centers, we can have various level of energy control system or various type of energy control system. First, we have regional load control center. Then we can have plant load control centers. So when we are talking about regional load control centers, it will decide the generation allocation to various generating station within the region on the basis of equal incremental operating cost, considering line losses as equal and frequency control in the region. So regional load control centers will be deciding how much generation. So we have if we talk about, we have a big main control system. Main control system will decide how much power to be generated by each region. And how power will be interchanged between the areas. So this is the basic operation of main ECC. Then we have regional load control centers. So it will be a regional load control centers. So on the basis of power generation requirement from that area, your regional load control centers will allocate to various generating units to generate the power on the basis of economical operation of the system, which will be based on the equal incremental operating cost, considering the line losses to be equal and frequency control available in the region. So this is the functioning of regional load control centers. And then we have, below this, we have this plant load control room or plant load control centers. It decides the allocation of generation of various unit in the plant on the basis of, so after it will allocate to various generating units. If you know, when we are talking about generating units, generating unit will be one plant, and in that plant also we have various generating units. So in that plant, this plant load control center will decide each generator. So we can say first we have main. It is total generation. Then we have various regions where we have various load dispatch. In each we have various generators generating power plants. These are your regional load control center. And in each load control center, we have different power plants. So for each power plant, we have plant load control room. And for that, from that, we have various generators unit which load is decided. So main ECC will decide how much load will be supplied by each of the area. Then regional load center will decide how much generation we require from each of the generating units. And then we have plant load control centers which will decide what generation to be done by each of the generator available in that plant. So the plant load control centers will decide the allocation of generation of various units in the plant on the basis of equal incremental operating cost of various units and minimizing the reactive power flow through the line, so to minimize line losses and maintain voltage level and frequency in the plant. So this is how this basic control centers will perform. So we have energy control centers, then we have regional load control centers, and then we will be having plant load control centers. So these are the various parts of the control units. So this is all general introduction of energy control centers. Then we will be in next class, we will be discuss about what are the various components which are used in the energy control centers. If you have any doubt with respect to energy control centers, you can ask. So if you don't have any,
Sir, इसमें